Alright, Team Rare. So we've got a question at hand which says a spring that obeys Hooke's law has a spring constant K. Show that the energy stored in the spring when it has been extended elastically by an amount x is given by this equation, which is work is equal to half kx squared. So how do you prove this? These are the following steps. Start. First, you have to write down these equations. You know that work is equal to force times distance. Mark this as your equation 1. Equation 2, you've got force is equal to ma. This is the second law of motion, Newton's second law of motion. This is equation 2, because a spring which has been extended, there is motion there, so there has to be some acceleration, so this equation matters. Then the next one, for spring constant, force of a spring constant, force of a spring is equal to negative kx, like this. That is the force, the restoring force. So you've got this equation, these equations. This is your equation 3. And we can go ahead and substitute. Where there is work there, we put Fd. Equation 1, substituting there, meaning we are going to have F times D is equal to half kx squared, like this. You see? And while there is force there, so d, the distance, can regard this as x. When we are looking at the motion of this spring, we consider this as a thing which has got a spring. It has got some form of distance which is stretched in the x direction. So where there is d, you put x. F x is equal to half kx squared, like that. Then where there is f, you put negative kx. So negative kx times x is equal to half kx squared, like this. So we've got this equation, but as you can see, when you do this, this and these will cancel themselves. So you have to find a proper way of doing this. So let's do this. We cancel this one, then we use equation 2. We substitute where there is force, we put ma. So this will be ma, like this, times x is equal to half kx squared. So kx squared, half k is equal to work. So there we are going to put w is equal to work, and you know work is Fd from equation 1. So you put Fd where there is work. At least you've got something making sense now. Fd, like this. Then from there, where there is force, put negative kx, because equation 3 states it. Equation 3 states that F is equal to negative kx. So where there is F, you put this, and where there is D, you put x. This is ma x is equal to negative kx times x, like this. Hope you are following. Then we can work out this. This will be equal to ma is equal to negative kx, because when we divide this by x, the x will disappear, like this. You remain with this equation here. And from here, that's where you get to understand something. Acceleration, you've got acceleration there, and acceleration happens due to time, change in velocity over time. So acceleration is equal to dv over dt, the derivative of velocity over the derivative of time. That's acceleration. Then velocity is equal to the derivative of the distance over the derivative of what? Time. So I think we can do this. We solve this one, substitute there. So here m times dv over dt is equal to negative k over x. So we want to introduce velocity in this equation. So the best way to do this is to multiply by a special one, something which will equal 1. And in this case, we will decide to multiply by dx over dx, because this will give you 1. It's just 1. It's a special one. So you multiply both sides, dx over dx, even this side dx over dx, like this. Then when you do this, here you align, make sure you consider you produce something which will give you velocity this side. So let me align it. This will be dx over dt m times dv over dx, like this. It's multiplication. This is allowed. I can do this. Then that side I'll have kx dx over dx, like this. Scroll down. Let's hope you are following. Then here, where there is dx dt, we are going to put v, because dx dt is equal to v. So this will be v times m times dv over dx is equal to negative k x dx over dx, like this. So when you multiply both sides by dx, you multiply this by dx, even this by dx, you'll find that this dx over here will be cancelled, even this cancel, even this will cancel. You're going to remain with this equation, v m dv is equal to negative kx dx. And from here you can integrate. Just introduce the integral signs, integrals, meaning this will be equal to the integral. M can come outside because it's a constant mass. This will be the integral of v dv is equal to minus k. K is a constant as well. X dx, like this. Then doing this, the integral of this will give us m times v squared over 2 plus some constant which I will name as C1 is equal to negative k x squared over 2 plus C2, like this. Then if I bring this one on this side, this will be mv squared over 2 plus kx squared over 2 is equal to C1 plus C2. So writing this equation will look like this: mv squared plus kx squared half, like this, is equal to C1 plus C2, like this. It's very simple. We just did a simple integration. Okay, so I can factorize this half. You can see because we've got things which are similar there. So half, this will be mv squared plus kx squared is equal to C1 plus C2. So doing this, then I can give you a hint like this: velocity. Okay, I'll start with the position. X is equal to a cos omega t, like this. This is the formula. Then when you differentiate this, it will give you velocity is equal to minus a sine omega t, like this. This is the velocity. So this is in meters and this is in meters per second. So we're going to substitute. Where there is x, we put this formula, and where there is v, we put that formula. This will give us something like this: half m, where there is v, we put negative a sine omega t squared plus k, where there is a, we put a cos omega t squared is equal to C1 plus C2. Then when you work out this, this will give you half m a squared sine squared omega t plus k a squared cos squared omega t, like this, is equal to C1 plus C2, like this. Then we consider at initial point, where t is equal to 0. We are going to put 0 where there is t. When we do that, this will be ma squared sine squared omega times 0, like this, plus ka squared cos squared omega times 0 is equal to, so this we can denote this. We say let C1 plus C2 be equal to M. So C1 plus C2 be equal to M, so that we can just be writing M here because it's some constant number. Or let me write E so that I don't disturb this. Okay, so this is equal to E. Let this be equal to E, like this, right? Okay, so going forward, if you multiply this, sine of 0 is equal to 0. 0 times this, so this part will be cancelled. It will be equal to 0 plus cos 0 is equal to 1. So ka, so we've got the half there because it was distributed evenly, like this. Half ka squared is equal to E, like this. Then amplitude just the same as x, so E is equal to half k x squared as you can see. E is now equal to the work we were given, which is equal to half k x squared. This is how you can prove this question and be given full marks on this one, because it has got all the procedure and the steps required. So let me just do this, try to reduce something so that you see the normal procedure. You see everything from where we started from. Let me reduce this. So this is what we've done. This is the procedure. Kindly check this out. This is the procedure. This is what we've done, and this is how you can prove this question. I hope you understand this. Shalom.